Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So today's guest is Professor Nils Thuerey. He's an associate professor at the Technical University of Munich, TUM, and has been a pioneer in physics-based deep learning. We had a really interesting discussion today on, first of all, some of his background. Very interesting that he actually won an Oscar working in the visual effects industry for movies after his postdoc and PhD, before he then turned to academia full time, which is kind of incredible actually, and is interesting because I've noticed the lessons learned from the visual effects industry in terms of photorealistic representations of the world is actually something we then talked right at the end of the podcast. So make sure you listen to the end about the link between foundation models and surrogates to world models. These world models that are being created essentially as a synthetic environment to train autonomous vehicles and robots. And we actually talked a lot about whether there needs to be more physics in these world models, which I actually thought was a very interesting discussion, and we only got to it at the end. But you know, he's been one of these people who was doing deep learning in the mid 2010s and early 2020s before ChatGPT and the sort of big rise. And it was interesting to hear him talk about how his work was looked in those times compared to now, and some of the barriers, you know, and skepticism maybe people had. He's also been someone who's really pioneered open source and pushing the boundaries of differentiable physics in some of the codes that him and his team has developed, and now have moved into both generating datasets like the SuperWing dataset, but also addressing the challenge of foundation models, also from a sort of PDE point of view in the latest Tadpole paper. So we kind of go through some of those topics around those different strategies of sort of PDE-based methods, you know, pre-training on those versus doing more the traditional, I guess, building out large data sets. We talk about the role of startups and industry and academia. Interesting to get his perspectives on that, and how all three can work together to solve some of these problems. And we also talk about the open source, why he's so pro open source, and how we think that can help progress the field along. He's actually contributed together with his team many important papers covering not just on fluids but also on the weather side, interesting, like WeatherBench. So I put a whole link, a list of papers in the chat notes that you can in the show notes that you can have a look at. But I really enjoyed this conversation. He's someone who is very modest in what he's done, but if you actually read his papers and look through, you can see he's been quite influential in steering these topics, and always seems to be one step ahead of where most of the field is at. And so if you look at his 20, 25 and 26 papers, you'll know what I mean by that. So hope you enjoy this episode with Professor Nils Thuerey. Well, thanks for joining today. I've been very keen to speak to you because as I've been getting up to speed myself over the past years on machine learning and differentiable side, your name is a constant, top of the list in terms of influential papers, in terms of doing things what seem to be earlier than most others have done, setting the scene, which suggests to me that you have quite a good outlook and thought on it. So, thanks very much for joining. And, maybe as a starting question, you took a diversion, well, not diversion, but you spent some time doing visual effects after your PhD and postdoc. maybe what did you do your PhD? What was the postdoc? And then I'm intrigued on the movie stuff.
Thanks for the invite, first of all, Neil. Yeah, I'd be happy to chat about this. My background, or over my career, I have switched fields a couple of times. So my PhD was in a computational numerics, computational physics lab, basically targeting multi-grid methods and fluids. And then I switched to computer graphics for a while. I guess that actually was one of my motivations from the start. I guess I'm a visual person. I'd like to see how things evolve. And I think that's still actually one of the main things that fascinate me about fluids, these swirling motions and the things that actually do come out once it's working. So we also worked on computer graphics, basically for computer-based animation for quite a while, my postdoc at ETH. And then afterwards also did actually work in industry for a while because I was curious how things would actually work out in industry in a practical environment, and partially also because I couldn't really get a good faculty position at the time. Not completely voluntary in a way, but it was good to see. In the end, I noticed for me, research is the better field. But yes, that's why I did my postdoc basically. And then I think by now, actually 10 years ago, we started looking at machine learning. So previously we did in this ETH group what was called data-driven approaches in computer graphics, essentially also trying to work with data and somewhat aligned, but we didn't have the tools back then. So it didn't really work, to be honest. But we tried. And then when AlphaGo came along, I thought, this has to be something that works. I didn't understand it at the time, but I thought there's got to be something there. And then, since 10 years, I think we've been working on basically applying these techniques to numerical simulations and fluid mechanics specifically. And I think in a way it's a good time at the moment. It's finally starting to work, but it took a while.
So you then joined TUM and you've been there ever since. That was your period. And so where did you... what was it like? I'm trying to put it into the picture because it's very hard for people who were working on these things before now, before ChatGPT. What was the field like? What was the community like? What was the reception like when you were bringing up ideas of sort of data-driven and machine learning? Was there a lot of skepticism and pushback?
Yes, actually there was. Initially, especially in the early phases, all these AI, back then it was called deep learning techniques, were focusing on learning descriptors. I remember our very first papers in graphics, they basically couldn't synthesize anything. You learned some reduced representation that told you about what happens in high-dimensional data, but it couldn't really generate anything. Also, if you think about AlphaGo, the early success stories, it was basically 8x8 with 3 states. That's a tiny domain and a tiny state space. And back then that was challenging. So in a way, it really couldn't do much. And I remember quite well talking to colleagues and telling them, look, we're interested in this deep learning stuff. We're doing simulations. And then some of my colleagues literally laughed me in the face, like, you're doing learning for PDEs? What could be more ridiculous? If you have a PDE and you can solve it, why on earth would you do anything learning based? And I think so. There was a lot of skepticism. For years, I always had to defend in the very first slides of my talks that this makes sense at all. At least it makes sense to consider this combination. And luckily, interestingly, I think for the wide community, I think the picture really changed with ChatGPT. I think in computer science and computational fields, people have been aware earlier, but since ChatGPT, it's really on everybody's plate and in everybody's view, but before.
But you were, interestingly, I was looking through some of the papers, and you had slightly earlier on, probably some of the first ones I saw, like in the AIAA, the deep learning of some RANs of airfoils, and so quite a few in the 2020s before ChatGPT. So what was it like, sort of pre and post? Was the issue partly the compute side? Was it the architectures? What was holding back?
Exactly. The architectures were a fundamental issue I think the whole infrastructure. Right in the beginning, CNNs were a big breakthrough before you had the MLP. So CNNs definitely for field-like data work quite nicely. But also this shift from basically computer graphics to things like aerodynamics, the A paper you mentioned, were a bit motivated by the observation that it's really tough to synthesize stuff in 3D plus time. You essentially have 4D fields, even if you simplify it and treat regular geometries, regular grids. This is really difficult to do. It's still challenging these days, actually, with neural networks. So back then it was pretty much out of the question to do this. And in graphics, you actually have extremely good approximations that aim for the visual aspect of things. So it was extremely tough to compete with that. And interestingly, in the computer graphics field, also, if you cannot directly apply it on a scale and with a fidelity that's fit for movies, then your papers typically get rejected. It's computer graphics, makes sense, but it needs to look good in the end. With 2D proof of concept simulations, even if they were fairly accurate, you couldn't do much. It had to be movie quality basically, and that just was extremely difficult. Only possible for niche applications like super resolution. This was one that worked quite nicely, but they can look at repeating structures and in very local fields. For synthesis on larger scales, it was basically not possible. And that's why we also started actually doing these proof of concept papers, like the RANS predictions for AIAA. Back then, also these were tiny resolutions, 32, 128 square, basically, so very small domains. And also, I remember back then, actually, I'm glad it got into AIAA, but there were also critical questions even back then. Why would you even do this at all? This is crude approximations. Does this make sense?
Yeah.
But yeah, basically, we noticed in aerodynamics and in engineering applications, there's much more demand for getting things right and really going for converged and solutions that are accurate and can be evaluated. And there are many problems there that are really important, basically for a variety of industries. So we basically switched from graphics, trying to apply these for engineering applications.
And where did the PhiFlow and the sort of differentiable physics, where did that start to come into the grid? Because that seems to be now quite a hot topic, but you were publishing in 2020 on these. So where did that first come from?
I don't even remember. It seemed like a very obvious thing. We were working on computational numerical methods. The networks couldn't really generate a whole simulation. So why not start with a simulator, combining it with the network, and then if you want to get a gradient through it, actually need differentiability on the solver side. And the available ones couldn't do this, so we just started experimenting with own solvers. This PhiFlow became a good testing ground for very basic methods across different APIs. Back then, there was TensorFlow and PyTorch and JAX and the whole bandwidth of different methods. So I think it was good for experimentation and flexibility. And then ultimately we noticed it's a certain trade-off. Flexibility and generality don't go too well together. So now we're specializing a bit more, but PhiFlow was one of these early testing grounds. But for us, it really seemed like in a way, obvious way to go. And then later we noticed, there's actually quite some work to do and also interesting questions. How do you get gradients through long chains of solver operations, which is still a topic.
Maybe shifting a little bit towards what's going on right now. There's two fundamental questions that I see you've also been trying to tackle. I'd be interested to get your thoughts on it. And that is around, I guess, the foundation model topic, the idea of, I guess it's logical, isn't it? You look at ChatGPT and you see it as essentially a data-driven problem that, apply enough data, have a decent architecture, and you solve it. But two questions. One was on the idea of the ground truth, and can you ever surpass the ground truth? And, one of your recent papers looked at, can the model do better than essentially the quality of the training data? And the second one is more just a general question on where you see the likelihood of foundation models going. How realistic is it? But on the first one, maybe you could explain that paper, because that really intrigued me, actually.
Right. There was actually a brilliant observation by Felix, one of the PhD students from my group, that he noticed in some situations, he also looked at basic combinations of solvers and networks, and that the networks really seem to give extremely good situations, in certain situations, extremely good results that seem to be even better than the training data we essentially used for these cases. And looking into it a bit more, it's unfortunately not a topic that I think can be generally applied. And when analyzing it in terms of numerical errors and how these pieces fit together, it's basically a combination of the priors imposed by neural networks in terms of smoothness, in terms of being able to over-sharpen or reproduce and be trained for producing certain parts of the solutions that benefit the outcome. So in a way, if you can leverage, or if you understand your solutions enough to leverage these particular behaviors of neural networks, then basically the outputs can be better than what you trained with. But it's really this interplay of what neural networks do as essentially also numerical methods to compute a solution, and what's in your data and what you like to get out. So it raises some interesting questions on how to evaluate it, because if, especially in the numerical field, we're trusting the ground truths, there are also typically approximation errors in there. And it can actually happen that solutions output by a network might be even better if you consider other solves or other ways to approximate the same problems. But I think we also for this paper thought about it. It is very difficult to really do this in a targeted way. So we had some neat cases where it worked for some basic advection fusion, and Burger's equation was a good example, actually, in terms of the shock representation and smoothness. Burger's equation is non-trivial, but seemed to be a very good showcase for this. Directly applying it to other scenarios is challenging. So we haven't, unfortunately, haven't gotten around to finding a good way to leverage this for real-world Navier-Stokes problems or so. Right. But
what about foundation models in general? Like, how is your group tackling this? What's your strategy, in a sense? Where do you see this going?
Recently, we switched pretty much from these differentiable solvers to foundation models. I was quite skeptical for quite a while. I think there's also still quite some skepticism talking to other people in the field with foundation models. I think partially it's because of the name, right? Foundation model sounds super general, and I'm sure you and most people know these fields of PDEs are extremely diverse. The thought of having one model that just is everything out of the box is a bit unbelievable, and I think also still quite a bit out of reach. Nonetheless, if you just foundation was also by now, I think it's actually not so well defined. People use it in all various forms, and where I think it makes a lot of sense. And in a way, it's also the direction we are typically tackling, is to see it as a model that's pre-trained on something and then applicable to other tasks, other problems. So there's just some disparity between training data and the actual application. We want models to generalize. Also, generalization is not a well-defined topic, right? It's in distribution is clear, but how far out of distribution you need to go to have proper generalization, it's completely open. But in the past, that's been really tricky. In a way, it's a classical transfer learning problem. Now, I think with these foundation model tools, borrowing a lot from large language models, we can actually do this, that we pre-train on one part and then apply it to something else. And how different is up for very specific to problems and application domains. But that seems to work. And specifically what I'm quite excited about is that we notice you can actually pre-train on very cheaply generated data. Or for us, training foundation models in 3D plus time with the amounts of data needed seems very scary and also somewhat impractical given the current cost of doing these training runs. But we noticed that in a way you don't really need these huge amounts of data. And I think that really changes the picture, that changes how we can approach foundation model training. And I think in a way makes it much more attractive as a starting point.
Could you maybe go into a little bit more detail when you talk about not needing as much data or high quality data?
Right. So you also thought about this quite a bit, right? Your recent paper discussing the scaling of data and compute requirements for fluids is a good starting point to think about it. What we noticed in this Tadpole work, we called it typically, was basically that if you have a good solver, so it is actually also based in a way on previous work on this APEBench benchmark with very synthetic data. So if you take the right solver, these spectral solvers, then you can extremely efficiently compute super good solutions for a class of basic PDEs, advection diffusion, these ETD-RK solvers. In a way, they're really perfect. So also doing learning on this level does not really make sense because the solvers are so good, the errors are so low. You can prove that they are basically as accurate as it gets for these basic solutions. So we can basically generate this data extremely quickly and very broadly if you vary the parameters. And we noticed that you can then pre-train a model with this, just generating a lot of different solutions for varying parameter ranges for these different PDEs, from advection diffusion to transport to some higher order terms with chaos, Komoter-Zielinski, and some polynomial chemical reaction-like constraints. And basically pre-training these models on this very broad class of very basic synthetic solutions, nonetheless, is actually not a very easy task, and benefit, or seems to benefit in quite a bit of downstream tasks. And the nice thing then is, these solutions to these synthetic problems are really not interesting in a way. You can compute them almost as quickly with a solver from scratch, basically. So you can train with it, you can run it through a model to get a gradient, basically, but then you can throw it away. So it's basically just running the solver alongside. We typically have a node with 4 GPUs. So one GPU does the data generation, the other 3 train, and just generates data on the fly, throws it away right after, and produces more data. But the nice thing is it's produced on the fly, and it's really just a continuous stream of data to train with. You don't have limitations on the bandwidth side, on the hardware, disk space to manage, tens of terabytes or hundreds of terabytes to upload to HPC centers.
Yeah.
For anyone who's tried this, it's very painful actually to do this, and not trivial. So, having this online data generation with the training is really quite neat and worked quite well in our experiments.
But how do you see that progressing? I mean, I think this has often been my challenges, and you've been on both sides of it. One side of it is, let's take realistic. If we assume that the model should work for industrial scale problems, then the idea is you generate data like you did with the SuperWing or now this high lift error ML or a company generating data, and then you train on that, and that is one argument. The other one is you're starting from the far left side of basic PDEs, but where do you see? How can they go in the middle? The basic PDEs are just, can you go to Navier-Stokes? How does that scale to more complexity?
Yeah. So what we basically notice is that even if we pre-train those, so one of the tricks basically that I didn't mention just now was also that we don't train for a time evolution. It's really more of a latent space representation that is learned for single spatial fields. So there's no time in the pre-training. And then the basic architecture is basically so general that you can just put time on top of that, right? So you learn in this latent space one step to the next. seems to work nicely. And also time in a way is also a specific application already, I would argue, right? There are steady state problems that essentially go for an equilibrium already, or an average solution, where time does not really, the evolution of time doesn't really play a role. It's more a mapping of some initial conditions in the geometry or so to the steady state. You might need time in other solutions, other occasions where you really want to resolve what happens over time. But in a way, taking that out of pre-training already makes sense in retrospect, I think. And then with the synthetic PDEs, probably you also might not get the out-of-the-box best accuracy for high accuracy aerodynamic predictions. But I think it seems to be a very good starting point also for Navier-Stokes. So what I see as a practical kind of approach in the future would be to pre-train some very generic models as a starting point, and then step by step with further pre-training stages, move towards more application-specific models, aerodynamics maybe, other one maybe aeroacoustics, right? Other one maybe structural problems, or basically branch off different directions. But pre-training doesn't need to be restricted to these canonical PDEs, but could go in certain stages. And then at a company, you might, for a certain use case, then have 10 final models to fine-tune the last one for a certain application. I just think just this outlook of basically not starting from scratch, but pre-training and then downstream needing less data, I think is potentially a good
way. So because of that, do you feel that there can be, how general can these models go, do you think? If you put a looking glass.
Admittedly, that's an open question. And in a way, also, we were surprised that the models can learn something useful from these admittedly relatively useless synthetic solutions. But it's a really interesting question to analyze what they actually learn. So we had some hypotheses. Basically, do they really just learn more or less random abstract fields or physical structures like the key modes, or do they learn differential operators? Right? Also, these PDEs are built from certain derivatives, and it's difficult to disentangle. But for example, the initial conditions are relatively easy to test. So if the PDEs are initialized, if you only train with these random fields, the models actually also learn something, but it clearly does less good on Navier-Stokes than if you pre-train with the PDEs. So basically, the transformation of initial conditions into actual states of a PDE seems to be beneficial. I think this is just the first step. It's actually not right now difficult to disentangle what they learned. And intuitively, I think the network currently don't has any reason to clearly disentangle modes or differential operators or so. Probably just mixes the most prominent structures that come up. But in a way, also, most of the problems we're dealing with in engineering and in real-world applications are typically built from certain building blocks. The differential equations, in a way, have a very limited vocabulary. So my guess is that the structures that come from these actually, in a way, can be pre-trained and then reused.
Yeah, and I guess the other, so maybe to put it in a nutshell, in terms of your research and your thinking, do you think it's better to go down this sort of PDE route with an integrated solver in the loop, rather than coming from the other direction, which is just generating lots and lots of, if we're trying to ultimately get to predict a wing, practically speaking, do you think it's better just to simulate 1 million wings in all different conditions, or to sort of build up from the ground from a sort of PDE based that maybe pre-trained, and then you go to more complex, because they still do feel like different directions to go.
Right. The PDEs definitely aim for generality in a way. I think also based on previous work, if your data set is large enough, if you have enough data to really train a large scale model specifically for the task you're interested in, I don't think you actually need these more generic starting points. So if you can do this, I think probably is not necessary. It's really more motivated by the practical constraints, I think, at the moment, that especially in 3D for large-scale PDEs, it's actually difficult to gather these really large collections.
Yeah. I'm kind of intrigued on that point, just because, as that fluids intelligence paper tried to point out, there is a certain economic challenge which is feels to be different than ChatGPT, where ChatGPT's cost does not really include the data, the token cost per se, and therefore it's all on the training side. And I still fundamentally wonder, is it massively inefficient? Because someone said to me, well, if you run cases, maybe I'll pose this question to you. So someone said, okay, so if you need to generate 2 million cases in order to fully scope out what is a reasonable definition of problems within fluids, so all possible planes and cars and data centers and all the rest of it, and then you use all that to train a model, haven't you already got the solution from CFD for most of these problems anyway? Because you probably run it. Like, where is it? Just you're almost so massively in distribution that you almost could just map that solution to a new. Yeah.
Right. Well, you're right. That might happen. So 2 million seems a little bit scarce for actual geometries, right? But if you could pre-train enough of them, I guess you could hope that any new one you run would actually just hit close to one of the existing samples, basically. Then I think a practical problem would still be that essentially you need to look up this data somehow, right? So these millions of simulations would probably be, I don't know how many petabyte or gigantic amounts of storage. So it could be beneficial to pre-train just to have a reduced compressed representation to be able to efficiently look up these data points. And maybe also give some smoothness in between, right? That even if your exact geometry is not in there, you get an in-between solution. So it could actually still be beneficial from a practical standpoint.
Yeah.
But yeah, given how difficult it is and the amounts of data involved with these online generated data sets, it seems that you can actually get away with much less data.
Yes.
So in a way, the hope would be that you do this as a first step, and then maybe you can get away with 1 million of full CFD simulations, or significantly less at least, to get to the same level of accuracy.
Practically, maybe one of the topics that also interests people, and be interested to see how, from a coding point of view, you've seen this progress. So you raised the point of generating the data, throwing it away because you're ultimately using it. So maybe you could talk a little bit more what you saw as the challenges from an implementation, from a coding point of view, because that's, I guess, also part of the problem. If everybody's generating these hundreds of thousands of cases offline and then trying to bring it into a model, that also seems quite inefficient.
Right. So the infrastructure work is quite substantial. I think it's getting better, also largely thanks to all the methodologies converging on this LLM transformer style processing, which probably is one of the reasons why now finally we're in a stage where it starts to work, because also we have the tools and outlooks how to scale things up to these larger resolutions. It's nonetheless still quite tricky in practice. So also in my group, it took quite a while to figure out how to put these pieces together, and there are numerous caveats and things that can go wrong. So actually, admittedly, one of the things we're still fighting with is the nonlinear scaling. So even with transformers, which are demonstrated to scale up to billions of parameters, if you take one model and you just increase the size of layers and the overall capacity, it's highly nonlinear. So it's not guaranteed to work if you rerun this just longer with an increased size. Most likely, you at least need to adjust the learning rate. The additional hyperparameters like smoothing of network states over time, how to actually adjust, how to scale up the size of the network in terms of this embedding space that the transformers have, or the weights for the additional components. That unfortunately, or it seems it's necessary to revisit for every new case again, and also for the PDE case, unfortunately. So it's still not really trivial to do this. And then also just admittedly, we fought quite a bit just with the data management. So we rely on these official compute infrastructures. Here from Bavaria and Germany, we now have supercomputers with a fair number of GPUs. But you somehow need to get the data over there, and then you can just store it on temporary drives. And if you don't pay attention, then suddenly your trainer data is gone. If you don't train often enough, and issues like this, basically.
But how did you solve that with some of the? Just wanted to double click on the, 1 GPU to generate the data, 3 to train. How were you getting around the passing the data between? I'm just trying to learn a little bit more how you approach that topic of the online training.
With the online training, so the classic approach would be you have your huge data set on disk, and eventually, if you don't want to overfit to what fits into memory, you somehow need to get it from the disk, get it to the GPUs. With this large data set, that becomes a bottleneck, at least for even if you have hundreds of millions of parameters. On HPC systems, I think we notice especially the hardware, the interconnects are good, but not fast enough to really get the data in quickly enough for training. So the standard setup would be, you have your GPUs, they need to load the data from this, then shuffle it through the network to get a gradient, and then need to load the next sample, basically. And for this online training, we are already basically forced to deal with a separate process that does the generation. So it's natural to put a buffer in between. So you basically have a buffer that is filled up by the simulator, and then the training threads just pull the data from there, or basically take a random sample that's available, then train with it, and we try to replace it as quickly as possible. So in practice, this doesn't guarantee every sample is used only once, but you can measure the throughput of your simulator versus the training, and it's typically at least below 2. So somewhere between 1.5. Some of the samples get reused before they get replaced. But
so did you? That's interesting. I mean, I need to look a little bit more at the paper and the code, but that was the bit that I guess I was assuming maybe for your PDE problem it's easier. But if we're doing what is, let's say, if we want to have something really accurate and we're doing an LES simulation, the actual LES simulation might need to run on 64 GPUs for 8 hours. But the training is obviously way faster than that. So do you have any thoughts on how you would balance from a loading point of view?
So my guess is that's why this online training so far hasn't really taken off before, because like you mentioned, for all classic simulations, exactly, you have the warm-up time until you hit some equilibrium that's physically valid. And that could be used, and it might take for a realistic real-world case might take hours until you're in that regime, and need fair number of CPUs at least, or GPUs if you have a modern solver. So that's really unattractive, because the speed of generating the data is way below what you need for training, which is why I think it's actually so interesting to use these canonical PDEs with these spectral solvers, because it's really, the solver is basically as fast as a network. Or typically we run, actually the training we run on little regions like 64 cubed, and the solver typically produces larger ones like 256 or so. And even those are pretty close to the training speed, and then you can basically cut out different pieces for data augmentation. But it matches quite nicely. So I think without such a solver, doing a large-scale pre-training is infeasible. I think there are some approaches doing this, but if you want to match the generation capacity, with the training capacity, you would need probably a supercomputer to generate data on the fly just to feed a decent-sized model.
Yeah, then my other thought was actually, whilst it takes 8 hours on 64 GPUs, let's say, to do it, that is the entire simulation. But actually to generate one time step is probably only a second or 2 seconds. So part of my interest, and maybe some groups are already doing this, is training per time step. Now, the variation from one time step to another is pretty minimal. So you could argue that you're not really learning that much between, but you are. That's the only way I could see that the time scales being similar, which I guess ultimately addresses one of the challenges that I think many people have, which is almost all of the standard data sets and standard machine learning approaches do take some time averaged solution, which if you're trying to get to real problems and real accuracy, turbulence is transient, and giving just a steady state answer or time average answer is, not really representing the ultimate goal of, like, weather forecasting. I guess you would have the temporal evolution of it. So I don't know how we can get over that issue.
I think it's a great outlook to really target time. I think there are some, probably from what I've seen, there are quite some hurdles for practitioners because we have all these pipelines set up for averaged quantities. All right, potentially, I think this would be neat to have in place. Regarding your first point, though, with the exploiting the fast solves over time for data generation, unfortunately, here with Tadpole, with this online training, we have some data that is pointing to problems there. So what we noticed, even with this online generation, if we don't replace the data fast enough, so if this reuse is too high of our pre-trained buffer, basically, the models do start to overfit. So typically, for foundation models, you're dealing with fairly large models. So ours are not even extreme, but on the order of maybe 100 billion parameters. And if the samples are reused too often, the models already, we saw some signs of performance deteriorating if the generator didn't catch up. And basically, this was just out of pure luck because of scheduling on these high performance systems. If there's one of the GPUs is for some reason slower, and suddenly on one training run you reuse the data more often, we saw a drop in performance. And even there, the correlation between the samples was not overly strong. So it's still generated a fair amount of data. But I would be worried if we have these strongly correlated samples over time.
Yeah.
Even if you're able to swap them out and reload different configurations for a solver, I think this would be difficult to ensure that the variability in the data is large enough to not overfit a large model.
Yeah, that's a very good point. Actually, that's again, the drawback that the temporal evolution of the PDE needs to be small for numerical reasons, to avoid blowing up, because of the CFL constraints, etc. So you're kind of forced to slowly march in time. Whereas I guess you're right. If you feed the machine learning model that, it's just going to keep seeing essentially the same solution.
Very similar ones, yeah.
That's but that's where I still see a bit of a fundamental. I just don't see. That's why I see it almost as. That's why I was interested in your differentiable physics, your code writing, essentially, because I feel some of the breakthroughs in this probably will come through a clever use of the training being linked to the data generation in a way that, I
think right now our focus is on foundation models. I'm also confident that at some point it's going to make sense to bring the solvers back.
Yeah.
In our tests back then, a few years ago, basically did pretty clearly show if you have a solver that does anything decent, the learning task is just simpler. So once we have kind of reached the at least a reasonable capacity for this pre-training, I think it might make a lot of sense to put a solver back into the loop to just make it more accurate in the end.
Yes.
Also, it is challenging at the moment at the scope, given the current infrastructures and large scale models. It's typically challenging to just train a single model in a decent amount of time, and then trying to get a solver into the picture and maybe going over multiple time steps. Things like this are tricky. But it's also going to change next years.
Yeah, no, I would agree. And maybe the other topic is around what were some of your lessons learned from doing, WeatherBench and APEBench and some of these more benchmarking efforts? Because I guess that seems to have helped quite a bit on the weather and climate side. So what was some of the genesis behind those efforts?
So the WeatherBench effort, in retrospect, it's great that it's doing so well. I think it, especially, I guess, actually, think about it. So, what I'm trying to say is basically these benchmarks have a big impact in the field. I think by now that is widely accepted across all the fields. Back then, it was probably more clear in the vision area, where a fair number of benchmarks have been around for quite a while. But in other fields like weather, there was very little, basically. So having established benchmarks and reliable evaluations is really important for any discipline in the field. I think that's a nice pointer. And it's typically it's quite some work collecting the data, and thinking about what should be in there and how to evaluate it. So the way those efforts are, I think, really important for any subfield within any data-driven discipline. And I think by now it's great also in this scientific AI field that this is noticed, and that by now more and more benchmarks are coming out. I think that's really important.
You recently generated from your group the SuperWing data set. I mean, where do you see this going? And this is a little bit of a philosophical debate around data, because on one hand, you could argue that the progress in this field does seem limited by data to a certain extent. And, does it mean that there should be some coordinated effort to generate data? And if so, who should be doing that, and what should be the license attached to it, given that there is clearly also a commercial benefit to be had?
That's a good question. I mean, coming from a university, I think it's great if it's all public and as open as possible. But given the commercial interest, and also by now the clear outlook that this will be useful, it would of course be great to have support from commercial partners in this. I think it's getting better also. More and more companies see the need for AI, and then also the need for benchmarks and data sets on that front. So I think it's improving, but definitely an issue where things could be done and could improve a lot. And unfortunately, there's so much, to quickly wrap this up, but I think there's so much proprietary data with IP rights and so on that are probably on some servers and companies that cannot be used. So it probably needs an effort to generate data that's free and usable.
That I keep jumping between that, because on one hand you could say that it is a bit like maybe open science experiments, with astronomy or things where there's a sort of public good, and a lot of it is funded through taxpayers ultimately, through sort of science funding, and the data's made available. Part of it feels that would help all companies, to be doing it. But at the same time, is it really the responsibility of governments and science to do this? It's kind of one.
That's true. Could argue why the companies should pay for it if they benefit from it, right? But
I just look at, I don't know about you, but I look at all the supercomputers in Europe, just as an example. And you think, how much data could be generated, given that these systems now are quite large, because they're being scaled up for the task of also, large language model training, etc. If you've got a cluster with 10,000 GPUs, you think how much data could you generate, from fluid simulations with 10,000 GPUs, even just, for a few weeks or a month, that does feel like it could be a huge way of doing it. And if it's only a commercial company that does it, they probably have no incentive to release that data.
Right.
And it then becomes hard to progress the field if only one company has that data, where it feels like with large language models, the data has actually had quite an open movement, right? There's quite a lot of open data, obviously, around this. Mm-hmm. And so, yes, you still could say you can only make models if you've got lots of compute, but there is already a movement now with open source LLMs, going on. Whereas I feel now, how can there be a movement of open source surrogate models if the data is not there in an open way? It's
right. It's a good point. It would be a pity if that gets hidden away due to commercial interests. So
it's almost the progression of science, I guess. This is, I don't know if you've had this, and certainly now myself being a commercial company, or the last two companies that that I'm at, there is always this debate of open source versus commercial, and I still find that a tricky one. I wondered how you've seen it. At what point does it help everybody to be open source? Yeah.
Yes. Okay. Right. I have a good argument for open source from my career at least. We used to work in computer graphics basically with movie studios, and I remember was my postdoc, one of the first papers at one of the larger conference SIGGRAPH there. We basically put up with an open source code, and company DreamWorks at the time actually picked this up pretty quickly and directly used it for one of their shots. And we asked, can't we get, or maybe they can put us in the credits somewhere. They sent us a poster in the end, and also quite a few of my friends and kind of laugh, all right, look, all you got for this work, you put up your code, you got a poster for it, why did you sell it or so? A couple of years later, all these movies where it was used were one of the key things to apply for one of these tech Oscars. There's also application procedure, but in the end we could show, like, look, it's been used in all these movies. And this Oscar actually did help a lot also for applying for faculty positions and so on. So this is largely due to open source availability and just impact in the field. So I've had very good experience with this. And I'm actually very happy that now in the AI field, this is so obvious. Right? Also, 10, 15 years ago, it was it was actually the exception that papers came with code, and it's great it's changed so much.
Yeah, it does seem an interesting one, though, because it's, given the large amount of money that's required to develop models and develop training data, there has to be some route to that money coming back, which is why for a commercial company, if they spend $100 million on compute and they have to think, well, how am I going to make a business out of this? And so it's kind of an interesting one, that is the business that the value to the company is not the model, but how you sort of tweak the model, so to speak. And therefore, just because there's a foundation model out there, which is open source, the real value is that every single company needs to customize it, which I think is the value at the moment for open source LLMs, that ultimately companies still make money out of it because everybody realizes that it isn't fully ready in its base form, and that actually you take it and you tweak it and you optimize it, and so there's money still to be made. And that's what I kind of wonder on the fluids surrogate modeling side, or even beyond that. Would it still be in the interest of some company to make it, because ultimately the money will be made customizing it, and therefore being open helps the whole community to develop it faster and make it more competitive against closed models.
Right. That's definitely my hope that we can go towards some foundation models or some generalizing models in the field that can then be fine-tuned and adapted to different applications quite easily. I think that's been super useful in the LLM field, and I do see potential there on the PDE front and fluids front. So, and I think if at some point it's clear that you can get a really good result, right? If you actually download this model and then fine tune it on your couple of wing data set cases or so for a certain regime you're interested in, then there could be a clear commercial also benefit for a company and a clear use case of supporting these open models.
Yeah.
So that you could imagine an infrastructure environment working quite well also in this area. But that definitely needs a coordinated and a large-scale effort to build it up right now.
That seems like there's lots of separate efforts, I guess, going on, but not one coordinated. I mean, maybe moving to some of the final questions for you is I guess a couple of things. Before we get to the future-looking one, I'm just interested, where's your side on the startups or academia industry? Because I've noticed there's a lot of, in recent years, there's even more interest in startups and the value of startups, but then that also in some ways can conflict with the open source academic mindset. Where have you seen that in the world? Have you been tempted with startups of industry? Where do you see that role of academia, startups, and industry?
Yeah, it's a good question. Exactly. Especially in the last 1 or 2 years, we've seen a very nice rise, I think, in terms of funding and also just founding of all kinds of spin-off companies or pivots of existing companies towards this physics AI direction. So, I think also in a way confirmation that now it's really starting to work. Right, it's ready for practical applications. I've definitely toyed with the idea so far, or also on my side, there are no immediate plans for this. In a way, I had my experience with industry for visual effects, and before, I'm quite happy with the open university research side. So I've always been a big fan of open source and just being able to put out things. And for research, I mean, it's also effectively a market with this openness and impact, right? If you can generate this, later on you can say, look, give me more money for research to do more of this. So it's not the commercial market, but also have our own market in terms of research money. But I like the openness of that. So for now, I think for me, that's personally just because I like this openness, the better direction. But we're working with all kinds of companies due to the commercial interest.
Yeah.
But we were basically trying to do this on the more open university side and then work with individual companies for maybe adopting or adapting these techniques.
Yeah, I was going to say, because the danger is if all top academics create startups, then there will be no academics left to do the sort of. So that I'm sure that has been discussed a little bit in the broader LLM space. If the only companies doing the latest stuff because of the scale are the big tech companies, then there is a risk to open science, I guess, because everyone's tempted to go to a commercial company that maybe aren't, as you said, incentivized to be open. I guess as academia, you are incentivized to be open because the reward structure is based around it, publishing, grant money. Like if everything's closed, I guess it may help the university a little bit because of grant capture or something, but it's not really the core aim, is it?
It's difficult actually for universities. I think in the past, quite a few labs had their in-house solvers and then basically earned money and funding with direct, basically support or consulting contracts with companies. But right now, I think, especially in this fast-moving AI field, with closed solutions, you would see very little impact. At the moment, it definitely works nicely.
No, I think that's why I'm always championing the academic side, because I think people look at research coming out of tech companies or research coming out of companies, but forget that actually most of the things start in the university, most fundamental ideas, and they need to be kept being promoted. And that's where I feel the data is the issue, because if you don't have open data, then you can't actually, universities can't progress and can't publish and can't advance the state of the art. If everything's done closed door, it actually hurts progress, doesn't it?
So LLMs will be interesting to some extent, right? There have been initiatives of training open LLMs, but some of them, I guess, did fairly well, but the top models are not open. And right now, I think there are very few people who really can or try to train their own LLMs. That's really become a very tough field, at least, to operate in.
Yes. So where do you see, if you have your looking glass or your crystal ball, if we were to talk again in 5 years' time, where do you think the conversation will be going? What do you think will be the breakthrough moments? Do you feel that we're going to be just incrementally over the next 5 years, or do you perceive some big breakthroughs or leap?
I just hope that we're going to see this breakthrough in terms of adoption. So now also all these initiatives on commercial side, I think, point towards the field really starting to work. So I hope that in 5 years we really see widespread adoption for actual applications. In a way, sounds a bit boring, right? Just being used in practice, but I think, right, also working on this for almost 10 years, I think it's about time that we do see that that's really useful for real world things. So I just hope that now we're at a stage where this really can be pulled off. But I mean, the field is really progressing extremely quickly, and so one of the outlooks that I've been intrigued about are these world models, right? And like vision, by now they're already going beyond foundation models or specific language and just visual models towards models that just capture the whole world. And right, also vision now notices actually physics is an important part. You only see so much. A lot of the complexity comes from things you don't directly see, like air moving or so. I think that's a really interesting outlook to really simulate basically the whole world around us on a larger scale with the physics accurately. I think that could also be super useful for engineering and real applications in a bunch of areas. But getting that right seems like a whole different level on top of what we're currently dealing with, just only doing the physics right with the foundation models. But I think it's a really interesting outlook.
Yeah, that's actually a good point, Eddie. I forgot to ask you about that I still don't fully get. I mean, I understand the world models are obviously one very big use case is robotics, and driving, autonomous vehicles, and sort of giving that synthetic data to help them to operate in the world. The bit that I guess I'm less sure on, and I wonder whether economically and scientifically, is the physics side. Does it make a difference how good the physics is? Like, as long as it looks right, and this is why I'm interested, because your movie background, like, does it matter to the robots and to the autonomous vehicles?
Actually, I do think that, at least for robots, the physics play a big role, because ultimately the action that you're generating is the control, right, of the actuators, of the actual things that the robot should do. And you need to estimate surface properties, the weight of an object, weight distribution, stability, and all these things to, at least in a variable environment, to interact with the world. So I think for robots by now, right, rigid body type, or even somewhat deformable, and physics are playing quite a role. So I would guess that it does make a difference. For autonomous driving, we could argue at the end, you only need to detect, right, is a dangerous situation or would something have gone wrong? You can probably do a lot without having to go through the whole crash or actually simulating how the car would tumble or crash into a building or so. That might not be so important, right? As long as you can detect this would have gone wrong.
Yeah.
But for robots, actually having to really interact with objects, I can imagine it plays a larger role. And then again, looking towards fluids, I think a big challenge also in the current development pipelines is this interaction with the real world. I mean, I think in the end, the current validation and certification still goes through a lot of testing stages, and at the end you have all kinds of real world flights and experience to make sure that the systems really do what they should in the real world. But if you could shift some of that into an earlier stage, I think that could also be definitely interesting if you could have different environment conditions, different flow conditions, and you could have an object interact dynamically in such an environment.
Yeah, I guess maybe you're right to maybe the examples I've looked at, if you look at a robot walking around a factory floor or it has no the drag, the lift, the thermal properties are very second or third order effects. They don't really influence how it's performing. But I guess you're right. If it was like a drone in the sky or a boat in the water, then the physics actually do make quite a bit of a difference. And then I guess it really is depending what's the use of these world models. If they really are like a true representation of the world for that drone or helicopter or, I guess at the moment, the autonomous vehicle, you're right, it's more sensory. Like I see there's a person walking. It's not to design the car, right? It's not to say, I see now that in this real world, by changing the shape, the drag is lower because it's actually, I guess maybe that's where you're thinking, right? That the world model could be used as a true synthetic environment.
Right. Or cars, I guess. If you could simulate a rainy and stormy situation and then really get feedback on how the rain would splash around the car or how a gust of wind would influence driving stability in extreme conditions, or all kinds of landing and starting scenarios for planes. If you could really get feedback on how a whole deforming plane with changing conditions would behave, I think that's still beyond even regular simulation capabilities. That full structure interactions with changing conditions are really challenging. You could get some feedback on these, and then ideally put an optimization loop around them, right? You would want to actually optimize your wing profile or the shape of a vehicle to behavior in the whole longer sequence.
I feel like this is also the big debate, well, not a big debate, but a debate around the classic tool calling thing. Like, is an LLM good at adding numbers? No. So just go and call a calculator. That's like ultimately, I guess, if you call ChatGPT to add two numbers together, it's just calling a tool of a calculator and adding the two numbers together. I kind of wonder sometimes in this world of world models or optimizing, is it really that it's truly integrated into a world model, or is it more likely that there is a sort of agent workflow where it's calling a surrogate model, and maybe that's where they're two separate models, if you know what I mean, rather than just a world model. It's more of an agentic way, if you know what I mean.
Or not, that would already be a big step, right? If we had any visual model that could on demand call some physics sub-models, surrogates to get feedback on how these different pieces it recognized should interact. Or for rigid bodies, actually, these days, you would just call a rigid body simulator. You would probably not need a surrogate.
That's kind of where I'm always debating, and that's the traditional one that you said. If the solvers get so fast, like the spectral solver you mentioned, or now with advancements in GPUs, some people are saying I can do a simulation in a minute, and then you think, well, do I need a surrogate if the solver can run so fast?
Right. I think for world models, an interesting challenge will be to quickly switch from the approximate fidelity kind of for rigid bodies or the formal objects of wind or different feedbacks needed in the environment. Sure, if I know I need perfect rigid bodies for a certain case, that might be ideal, but right, I need some feedback on wind or how my plastic cup should deform or should it break, predictions across all these different physical phenomena. I could imagine that a flexible surrogate that at least gives a first prediction of estimate of what might happen there could be beneficial. I think that would be tricky to do with classical simulators.
Yes. Yeah. I think this is where it's the classic, what's the use case of real time? And sometimes if you go to an engineering team, and I've had this where you tell them that a surrogate model prediction in 1 second, sometimes they'll say, well, we don't need it to do it in 1 second. It's actually fine. If it takes 5 minutes or even half an hour, it's okay. It's not our bottleneck. Whereas I guess if it's integrated in a world model or something, you need it to be essentially real time, or else the whole value breaks of some simulation, like testing a car moving. If you have to sort of pause the simulator for 30 minutes, then it's not.
Then it would not feel right.
Yeah.
I mean, real time is extremely challenging. Then you need, I guess, to be a realistic virtual environment for a person. Yes, you need millisecond.
Yeah,
feedback.
real time. So, maybe a final question to you, looking more if there's a student listening to this or someone doing a PhD or early in their career, given all these changes, what would you recommend someone would study as a PhD topic? What's going to future-proof them in this world?
Maybe I'm biased here, but I think these are really important techniques. I do see a lot of potential for AI-based techniques. So I think it's important to have an understanding, to know the classic physics, numerics. But by now, within these numerical tools, I think AI is a super important component. So I could highly recommend looking at least combinations of classic and AI-based methods.
Mm-hmm.
And my guess is also that in the future or in the next couple of years, we were not going to be completely replaced by, I don't think ChatGPT is going to take over fluid simulation too soon. So having experts that really understand what's happening there, I think is going to be needed for quite a while. So
yes,
I think it's still a good field to work on.
Yeah, I guess that's the truth. I guess the short, medium, long term, I guess I see at least now the short term, there's even more need for specialists because frankly, it's almost become that simulation is more of a popular topic now. The fact that all these startups are getting funded, the fact that, there's more money in this space, there's more need to find, who's an expert in crash simulations, who's an expert in acoustics, who's an expert to help computer scientists, to develop these models. I guess it's only in the very long-term future that you could imagine maybe you don't need as many specialists because so much of that knowledge is now ingrained in these models. But in the short term, it's almost need more specialists to help. But deep specialists, I guess, who really understand it. That at least that's the way I'm seeing things at the moment.
And I think that's usually a great topic for a PhD, really getting to the bottom of things. Right? It's a nice opportunity to work on one topic for a couple of years and get as much understanding as possible. So right now, I think PhDs in this area are still a very good idea.
Yeah, no, I agree. Well, thank you so much for taking the time to speak. I find all these topics fascinating, and one of the things I'll do is put a list of the papers in the show notes because I think actually there's a lot more to gather from looking in the details and looking at the codes that your group did. So I know we didn't have time to cover all in full detail, but I'll put a list and hopefully people can find the time to read through the papers.
That's a good idea. Great discussion. Thanks for the invite.
Yeah.
Very interesting.
We'll speak again in 2 years' time and we'll see if the predictions are true.
That's very interesting. Good plan.
Thank you.
Yeah, thanks.